Imagine a world where the dangers of a powerful chemical like DDT were known from day one, and it was never unleashed globally. Welcome to our what-if scenario, a journey into an alternate history where humanity chose a profoundly different path, altering the very fabric of our shared future. The year is 1947. World War II has just ended, and the globe is slowly, painstakingly piecing itself back together. A palpable sense of hope for a healthier, more prosperous future permeates the air. At the heart of this post-war scientific renaissance is a young chemist, Paul Muller, working for the Swiss company Geigy. He stands on the cusp of a groundbreaking discovery: dichlorodiphenyl trichloroethane, or DDT. In his lab, he's witnessed its astonishing effectiveness as a contact poison against insects. In our timeline, this chemical became a celebrated miracle, widely credited with dramatically reducing malaria rates in countless regions and boosting agricultural yields. For decades, it was hailed as a cornerstone of public health and global food security. But what if, at the very moment of its triumph, an unseen yet critical piece of data emerged? Imagine if, concurrently with Muller's lab work, a more comprehensive, long-term toxicological study, perhaps initiated by a visionary, ecologically minded researcher within a rival firm, or even a nascent international scientific consortium funded by early environmental philanthropists, had already been underway. This parallel research wouldn't just focus on immediate insect mortality. It would rigorously track the chemical's persistence in soil and water, its accumulation in biological tissues, and its effects across trophic levels, even at minute concentrations. Dr. Elena Petrova, a Ukrainian biochemist who had fled the war to a research lab in Switzerland, had been meticulously tracing the metabolic pathways of similar halogenated compounds, noticing troubling persistence. Her colleague, Dr. Kenji Tanaka from Japan, cross-referenced this with emerging ecological models, predicting bioaccumulation with chilling accuracy. The findings were stark, undeniable, and presented with such scientific rigor that no government, no corporation could possibly ignore them. This isn't just a slight concern, it's a stark, unequivocal warning. DDT isn't just an insect killer, it's a persistent organic pollutant, a bioaccumulator that, even in trace amounts, causes devastating, irreversible harm to non-target species, particularly birds, fish, and in the long term, could pose significant threats to human endocrine systems. A confidential report leaked to a nascent international scientific journal with a strong ethical charter would trigger the alarm bells heard globally, forcing an immediate halt to its mass production and deployment. The immediate impact: a monumental worldwide re-evaluation of pesticide development. The scientific community, jolted by this irrefutable evidence, wouldn't just hesitate, it would recoil. Instead of a frantic rush to deploy DDT, a global scientific effort would pivot instantly. Billions in research funding, originally destined for the development and mass production of broad-spectrum pesticides, would now be directly channeled towards understanding complex ecosystems, fostering soil health, and developing truly sustainable agricultural practices. Humanity would embark on a global effort to perfect integrated pest management, IPM strategies, robust biological controls, and highly targeted, rapidly degrading chemical alternatives that leave no lasting footprint. This early shift would cultivate a generation of scientists with a holistic, ecological mindset from the outset, moving research from a reductionist view of single-species pests to a systemic understanding of environmental interactions and a deep respect for natural balances. University curricula would rapidly integrate ecotoxicology and systems biology as core disciplines, shaping how future generations of chemists, engineers, and agronomists approached problem solving. The environment at this alternate timeline would be profoundly breathtakingly different. Iconic species like the bald eagle, the peregrine falcon, and other majestic raptors whose populations plummeted in our world due to DDT accumulation would never face such an existential crisis. Their numbers would remain robust, their powerful wings soaring freely through cleaner skies, vibrant, living indicators of a healthier, less contaminated ecosystem. But the impact extends far beyond these charismatic birds. Beneficial insects, crucial pollinators like native bees and butterflies, would thrive unhindered, supporting richer plant biodiversity and healthier ecosystems. This, in turn, would lead to more resilient wildlands and robust agricultural yields, sustained by natural processes. Aquatic environments, from vast oceans to pristine freshwater lakes and vital estuaries, would escape the pervasive contamination that plagued our timeline. Fisheries would be abundant and untainted, teeming with life, from the smallest zooplankton to the largest apex predators. Coastal communities would not face the toxic algal blooms exacerbated by runoff from chemically intensive agriculture, as nutrient management in farming would also be prioritized. The subtle yet devastating chemical footprint that permeated every corner of our globe would be far less pervasive. Rachel Carson's seminal book, Silent Spring, which awakened our world to DDT's dangers in 1962, would never need to be written. The eerie silence she described would never have fallen. Why would it be? In this world, the spring would always sing, a chorus of thriving life, vibrant and unmarred. Beyond the absence of specific pollutants, this early environmental awareness would cascade into other areas. Policies around industrial waste, air pollution, and resource extraction would likely be more stringent from the beginning. Perhaps the concept of circular economy principles would emerge decades earlier, driven by a deeper understanding of material life cycles and unintended consequences. The very definition of progress would be re-evaluated, placing ecological sustainability on par with economic growth, not as an afterthought. Engineers would be trained to consider the full life cycle impact of their designs. Architects would prioritize sustainable materials and energy efficiency, leading to the early development of green building standards. The ripple effect of avoiding one major chemical mistake would fundamentally reorient technological development towards a more harmonious coexistence with nature, fostering a culture of environmental stewardship from the foundational years of the post-war boom. This shift would also influence the nascent nuclear power industry. While still pursued for energy, its waste management would be approached with an even greater degree of caution and long-term planning, given the precedent set by DDT's dangers. Materials science, instead of focusing on purely synthetic, disposable plastics, might shift its focus to biodegradable polymers and sustainable composites much earlier. The textile industry might prioritize natural fibers and closed-loop dyeing processes. The oceans in particular would be remarkably healthier. Without the massive influx of persistent chemicals, marine food webs would retain their integrity, leading to more resilient fish stocks and greater coral reef health. The subtle degradation of ecosystems due to widespread chemical use in our timeline, often invisible until too late, would simply not occur. Entire species, like certain insectivorous birds or specialized marine invertebrates that teetered on the brink in our history, would thrive here, strengthening ecosystems from the bottom up. But this path without DDT was not without its profound shadows. While nature undoubtedly thrived, the picture for public health presents a far more complex and challenging reality. Malaria, a disease that DDT effectively suppressed in many areas, would remain a more significant global health challenge. Vector control would rely more heavily on traditional, labor-intensive methods like diligent draining of swamps and stagnant water bodies, widespread and consistent use of mosquito nets, perhaps even more advanced, naturally insect-repellent versions developed with accelerated research. and the encouragement of natural predators like fish that consume mosquito larvae in aquatic environments. This would be alongside the accelerated development of alternative, safer insecticides that break down quickly and, crucially, more effective targeted vaccines. This could lead to higher rates of malaria and other vector-borne diseases in some regions, at least initially, until sustainable, non-toxic solutions were fully implemented and scaled. The global health community would face a different, perhaps slower, but ultimately more sustainable and ethical fight against these devastating diseases. Then, a formidable new challenge emerges, a stark reminder that nature finds a way and disease adapts. In the late 1950s or early 1960s, just as the world was adapting to these new ecological methods of pest control, a new, incredibly resilient strain of malaria sweeps through densely populated regions, particularly in Southeast Asia and parts of Africa. This mutated strain proves less susceptible to the traditional methods and nascent biological controls developed to date. Without the immediate, powerful chemical hammer of DDT, the fight against this burgeoning epidemic becomes a true, desperate race for survival. Hospitals overflow, public health systems strain under the weight. National economies, particularly in affected regions, face significant setbacks due to illness and lost productivity. Mortality rates, especially among children, would climb, leading to a profound global humanitarian crisis. This period would be marked by intense ethical debates. Was the initial choice to forego DDT truly correct, given the human cost? Public discourse would be fraught with emotional appeals from affected communities, urging a re-evaluation, while environmentalists would staunchly defend the long-term ecological benefits. This societal tension would be a defining characteristic of this alternate 20th century, forcing societies to confront difficult trade-offs with open eyes, sometimes with agonizing consequences. Consider the village of Mbingu in Tanzania in 1963. Mama Zawadi, a mother of 4, mourns her youngest, little Juba, taken by the new aggressive strain of malaria. Her other children, though feverish, cling to life under meticulously maintained mosquito nets, constantly mended by community health workers. Unlike in our history, there's no mass spraying of DDT. Instead, the entire village is involved in weekly ditch draining initiatives, children proudly pointing out mosquito larvae, while new fish species, specifically bred for mosquito control, are introduced into nearby ponds. International aid teams aren't just distributing quinine. They're bringing in new, rapidly evolving diagnostic kits developed by accelerated biotech research and training locals in community-level health surveillance. The fight is person to person, village by village, requiring immense resilience and communal effort. For every Juma lost, there are countless others saved by these integrated, sustainable methods. But the cost in human lives, particularly in the early decades, would be undeniably higher than in our DDT-laced past. The global news cycle, without the distraction of environmental degradation caused by DDT, would focus heavily on these ongoing humanitarian crises, fueling public demand for scientific breakthroughs and international cooperation. Newsreels would show dedicated scientists working around the clock rather than spraying planes. This public health crisis, however, forces global science to unite with unprecedented urgency and resources. It spurs breakthroughs in entirely new, highly targeted vaccines, developed using novel genetic research techniques pioneered under this intense pressure. Early research into mRNA-like technologies, driven by this dire need, could begin decades earlier than in our timeline, revolutionizing vaccinology. Concurrently, new forms of vector control emerge. Perhaps sterile insect technique, SIT, was perfected decades earlier, where large numbers of sterile male mosquitoes are released to mate with wild females, suppressing populations in a highly localized and environmentally benign way. or perhaps genetically modified mosquitoes, designed to be harmless to the environment but incapable of transmitting the parasite, are developed and deployed with careful ethical oversight and rigorous community engagement. This accelerated biotechnological development might even lead to breakthroughs in combating other vector-borne diseases like dengue and Zika far sooner than in our timeline, as research into vector-specific interventions becomes a global priority. It's a hard-won lesson, certainly, demanding immense resources and human ingenuity, but one that ultimately accelerates medical progress by decades, forcing humanity to develop more precise and sustainable solutions to disease, rather than relying on broad-spectrum assaults. The ethical debates around these new biotechnologies would be intense, but the sheer urgency of the malaria crisis would often push them forward, fostering a new era of bioengineering for global health that is deeply intertwined with environmental responsibility and community consent. Public health campaigns would become incredibly sophisticated, focusing on community engagement, education, and decentralized health systems to manage outbreaks without relying on a single, universal chemical solution. The very paradigm of global health shifts from eradication through brute force to sustainable management and long-term resilience, emphasizing prevention and ecosystem balance. Agriculture, too, would undergo a profound systemic transformation. Farmers would be compelled to develop a much deeper understanding of soil microbiology, complex crop rotation systems, and the intrinsic value of natural pest resistance within plant varieties. Agricultural research would focus heavily on breeding crops with inherent resistance to local pests, understanding complex beneficial insect populations, and developing agroecological systems that mimic natural processes. This would involve significant investment in plant genetics and ecological farming techniques, moving away from monocultures towards diverse, resilient farm ecosystems. The concept of polyculture and agroforestry would become mainstream, recognizing that diverse crops and integrated trees can enhance soil fertility, reduce pest pressure, and increase overall farm resilience. Farmers would learn to cultivate insect predators, introduce beneficial fungi, and master complex intercropping strategies to naturally deter pests. While initial yields might not have seen the same dramatic, immediate boosts as with the introduction of DDT-dependent agriculture, the long-term sustainability and resilience of agricultural systems would be significantly improved. This would lead to healthier soils, reduced erosion, enhanced biodiversity in agricultural landscapes, and drastically less reliance on external chemical inputs. Organic farming principles, instead of being a niche movement, might have become the widely accepted norm much earlier, fostering a different, more symbiotic relationship between humanity and its food sources. Farmers, once reliant on a spray schedule, would become stewards of complex ecological systems, their expertise valued for its depth rather than its efficiency of chemical application. This could also lead to a more localized and diversified food system, as regions adapt specific ecological farming practices to their unique climates and pest challenges, reducing reliance on global food chains and potentially enhancing regional food security and economic independence. The very concept of food aid might transform, focusing on knowledge transfer and ecological farming infrastructure, rather than just commodity distribution, fostering self-sufficiency. Consider the American Midwest in the 1970s. Instead of endless corn and soy monocultures, the landscape is a mosaic of diverse crops. Farmers like the Johnsons, who in our timeline might have struggled with pesticide resistance, are now experts in maintaining hedgerows to attract predatory wasps, rotating legumes to fix nitrogen naturally, and using sophisticated weather modeling to predict pest outbreaks and deploy targeted biological agents. Their yields are stable, their soil rich, and their land supports a far greater array of wildlife. The market demands locally sourced, ecologically grown produce, making sustainable farming not just an ethical choice, but an economically viable one. This decentralized agricultural system fosters stronger rural communities and a more direct connection between consumers and their food. The demand for synthetic fertilizers would also be significantly reduced, curbing runoff pollution and energy consumption. New agricultural technologies would focus on precision farming with biological inputs rather than broad chemical application. The tractor itself might evolve differently, incorporating advanced sensors for soil health and pest detection, rather than simply larger spraying booms. Universities would establish persuasive agroecology research centers, becoming hubs for innovation and farmer training. Education about food systems would emphasize seasonality, regional specialties, and the ecological footprint of dietary choices. Yet this shift wouldn't be without its social and economic ripples. Some rural communities, particularly those in developing nations that traditionally relied on quick chemical fixes for immediate crop protection and disease vector control, might initially face significant hardships and economic losses in the early years. This could spark social tensions, even widespread protests, as populations grapple with fluctuating harvests, disease outbreaks, and the steep learning curve of new, more nuanced farming and public health methods. Governments would face immense pressure to balance ecological ideals with immediate human needs. In response, governments and international organizations would be compelled to invest heavily in farmer education programs, robust, sustainable technology subsidies, and comprehensive social safety nets. This would involve massive international aid programs focused on knowledge transfer and ecological infrastructure, fundamentally reshaping global development strategies. Nations would form new alliances driven not by Cold War ideologies, but by shared environmental and health crises. The concept of ecological literacy would become a cornerstone of education, taught from early childhood to professional degrees, embedding an understanding of interconnected systems deep within the global consciousness. Urban planning would also evolve, with green cities becoming the ideal, integrating natural ecosystems, localized food production, and sustainable waste management systems directly into the urban fabric, creating healthier and more resilient urban environments. Architecture would prioritize passive design, natural ventilation, and green roofs, seamlessly blending the built environment with nature. Public transportation would be emphasized, and pedestrian-friendly zones would flourish, as cities embrace a less car-dependent, more human-centric design. The very concept of suburbia might develop differently, with a greater emphasis on local food production and shared green spaces rather than sprawling, chemically maintained lawns. This would naturally lead to more walkable, community-oriented neighborhoods, fostering stronger social ties and reducing reliance on fossil fuels. In this alternate history, humanity learns a crucial environmental lesson almost immediately. A lesson our timeline learned far too slowly and painfully, often after irreversible damage had been done. The quest for quick fixes is tempered by a deep, undeniable understanding of ecological consequences. This early, profound realization would infuse scientific endeavors, policy-making, and even public consciousness with a precautionary principle that permeates all future technological advancements. Every new chemical, every new industrial process, every new agricultural technique would be subjected to rigorous, long-term ecological impact assessments from its inception, becoming standard practice across the globe. This early adoption of ecological foresight would mean that other potential environmental disasters, the widespread use of Agent Orange, for instance, or other persistent pollutants like PCE, or even the unbridled use of CFs, might also be averted or significantly curtailed, as their long-term environmental impacts would be better understood and prioritized. The ozone layer might never have faced the same level of depletion, preventing countless cases of skin cancer and protecting delicate ecosystems. The concerns about microplastics would emerge earlier, spurring more aggressive research into truly biodegradable alternatives from the 1970s onwards. Even space exploration might be approached with greater caution regarding potential extraterrestrial contamination, applying the same rigorous risk assessment. The geopolitical landscape itself might look different. Nations united by the shared environmental threats and the complex, persistent challenge of disease without a magic bullet might foster deeper international cooperation earlier. Could this lead to a faster formation of truly powerful international bodies focused on global health and environmental governance, perhaps even predating the full complexities of the Cold War, or at least shaping it differently? Resources that in our world were poured into weapon development might be reallocated to biosciences, sustainable engineering, and ecological restoration, creating a different kind of global arms race, a race to innovate for planetary well-being and shared prosperity. This collective struggle for ecological balance and public health could forge stronger international bonds and a more unified global purpose, moving beyond narrow national interests. Ideologies of conquest of nature would be replaced by coexistence with nature. Diplomacy would often revolve around resource sharing, environmental protection treaties, and collaborative health initiatives. The notion of ecological debt would enter political discourse much earlier, shaping aid and trade policies. Global scientific conferences, initially focused on the malaria crisis, would evolve into broader platforms for sustainable development, becoming far more influential than in our timeline. This proactive stance would position humanity much better to address emerging global challenges like climate change when they eventually become undeniable. Early investment in renewable energy, driven by resource consciousness rather than just pollution concerns, could also begin decades earlier. It's a world where the air is cleaner, the water purer, and wildlife thrives unburdened by persistent pollutants. It's a world where we faced familiar health challenges and unforeseen ones in new, more mindful ways, ultimately achieving a deeper, more profound harmony with nature. This alternate path illuminates the immense power of foresight and the profound ripple effects of a single crucial decision. It's a powerful testament to the idea that sometimes the easy solution creates far more problems than it solves in the long run, and that foresight, even when challenging, can lead to a more resilient, healthier, and truly sustainable future for all life on Earth. The legacy of DDT's averted disaster would be a pervasive sense of humility in the face of nature and an unshakable commitment to truly understand the interconnectedness of all things before acting. This isn't just a story of what wasn't, but a hopeful vision of what could have been, born from a moment of early wisdom